Hi, my name is Avi and I'm a PhD student at UC Berkeley. Today I'll be talking about some of our recent work on extending and generalizing skills learned by reinforcement learning through use of large prior datasets. Consider a robot that has been trained using reinforcement learning to take an object out of an open drawer. It learns to grasp the object and pull it out. If the robot is then placed in a scene where the drawer is instead closed, it will likely fail to take the object out, since it has not seen the scenario or initial condition before. How can we learn policies using RL that can generalize to new initial conditions? This problem has been explored before, but in the context of animals instead of robots. Around a century or so ago, Wolfgang Kohler and associates conducted experiments in which they placed chimps in an enclosure with bananas hanging from the roof just out of their reach. A box was also placed in the enclosure around 6 feet or so away from the bananas. After some failed initial attempts to directly reach the bananas, one of the chimps took a break, seemingly in thought, and then stood up. He pushed the box to a spot below the bananas, climbed on top, and achieved its goal. A common explanation for this problem-solving behavior is that it's a process that is incompatible with trial and error learning or reinforcement learning, but must involve some kind of explicit model-based reasoning or planning. However, is this really the case? Is explicit logical reasoning the only possible explanation for such behavior? A few decades later, to shed some more light on this question, researchers conducted a similar set of experiments but with pigeons instead of chimps, and this is what they observed. A pigeon is placed in a box with a plastic likeness of a banana hanging in the top left corner, and there's also a small block in the vicinity. After some wandering around, the pigeon starts to push the block to below the banana. It doesn't quite make it on the first attempt, but it tries. It pecks the block so as to push it right below the banana. It gets on top of the block, and it's finally able to peck the banana through the block. Of course, pecking plastic bananas and pushing blocks are not natural pigeon behaviors, so the pigeons in this study were previously trained by reinforcement learning of a different kind to push blocks and peck bananas. However, what's interesting is that these two behaviors were reinforced independently of each other. The pushing behavior was never reinforced in the presence of the banana, and all previous interactions with pecking the banana did not require any prior pushing. However, when placed in a new scenario requiring composing these two behaviors, the pigeons were able to solve this new problem in a zero-shot manner. Coming back to our drawer example, a simple new initial condition might consist simply of a closed drawer. That is, you need to open the drawer before you can take an object out of the drawer. More complicated new initial conditions in which the drawer is blocked by an object or by another drawer are also possible. We would like to enable our learn policy to execute the task from as many different initial conditions as possible. In this paper, we propose to extend skills learned by RL through leveraging past experiences, not too dissimilar to the pigeons. While task-specific experiences consist of behaviors directly relevant for the task, the prior dataset can consist of a number of random or scripted behaviors being executed in the same environment. If a subset of this prior dataset is useful for extending our skill, we can leverage it for learning a policy that can solve the task from new initial conditions. Note that not all prior data has to be useful for the downstream task, and we don't need this prior dataset to have any explicit labels or rewards either. We can now formalize a problem setting. The input to our method consists of two distinct types of datasets. The first dataset is a task-specific dataset and is labeled with sparse rewards, similar to standard reinforcement learning. The second dataset consists of unlabeled interaction data with no associated reward labels whatsoever. This dataset need not contain any interaction with the task object of interest, and not all of this data needs to be useful for the downstream task. Our goal is to utilize both prior data and task data to learn a policy pi that can execute the task from initial conditions that were unseen in the task data. In this paper, we primarily operate in an offline reinforcement learning setting, making use of only previously collected datasets. We start by running Q-learning on the task data, which allows for Q values to propagate from high reward states to states that are further back from the goal. This is analogous to the pigeons being trained to peck the plastic banana without having to push the block. We then add the prior dataset to the replay buffer, assigning all transitions a zero reward. Further dynamic programming on this expanded dataset allows Q values to propagate to initial conditions that were unseen in the task data. This is similar to the pigeons being trained to push blocks, but with one significant difference. While some directional pushing behavior had to be explicitly reinforced for the pigeons, our RL agent can incorporate past experiences without any explicit rewards being provided for this experience, letting dynamic programming do all the heavy lifting. We now obtain a policy that can solve the task from new initial conditions. Note that there is no single trajectory in our dataset that solves the entire task from this new starting condition, but Q-learning allows us to stitch together relevant trajectories from prior and task data without any additional supervision. The final behavior is reminiscent of the pigeon from the start of this talk, whose past experiences helped it solve a novel problem without ever being explicitly trained on this new problem. Let us first visualize the policies that are learned without any prior data. We see that the policy is able to successfully execute the task from initial conditions that were seen in the training set, but fails to solve the task from unseen initial conditions. We now visualize the performance of the policy learned by our method. We see that in addition to solving the task from seen initial conditions, the policy is also able to execute the task from unseen initial conditions, which indicates that our method is successfully able to leverage our unlabeled prior dataset. We compare our method to prior works that incorporate prior data, such as initializing from behavior cloning. We see that for novel initial conditions, such as where the drawer is blocked by an object, only our method is able to consistently solve the task. There is a comparison between our method and previous works for another new initial condition, where the bottom drawer is blocked by the top drawer from being opened. Once again, our method is able to solve the task consistently. Here is a summary of our results, where we see that our method is the only one that is able to obtain a high success rate even for all the unseen initial conditions. While we're able to obtain success rates of around 70% from offline training alone, our method is also amenable to online fine-tuning. We see that for all of the normal initial conditions for the drawer task, the fine-tuned policy is able to achieve a success rate of over 90%. We also evaluate our method on a real robot, where we see that our learned policy is able to open a drawer and take an object out, even though it never saw a single trajectory executing the entire task during training. Our method succeeds on 7 out of 8 trials, while our strongest baseline based on behavior cloning was unable to solve the task even for a single trial. Here are some example rollouts from our learned policy. In this work, we showed how model-free RL can utilize prior data to extend and generalize learned skills, effectively stitching together behaviors to solve problems in new scenarios. This sort of composition of skills is typically seen as the domain of model-based planning, but our approach suggests that such seemingly complex multi-stage behaviors could emerge automatically as a consequence of model-free RL with the right training data. Our initial exploration of these ideas leaves considerable room for future work. In particular, we believe our method can be an effective component of a lifelong learning system where every new learned behavior also utilizes prior data to learn and improve policy. More broadly, we believe that further exploration into the ways that model-free RL methods can enable acquisition of implicit mechanical models of the world is a promising direction for data-driven RL. We have released all code, environments, and datasets used in our experiments. Our implementation, which utilizes the conservative Q-learning algorithm, is likely to be of particular interest to those who are looking to solve offline RL tasks involving image observations and continuous action spaces. Thank you, and I'll be happy to take any questions.